10.4 notes, polar coordinate graphs, page 2. So now we're going to do the same thing we did just a minute ago, except we want to check or test the equation r equals 2 cosine theta for symmetry. And so, same way we started it before, I'm going to check for symmetry with respect to the line theta equals pi over 2. Remember, that is our vertical axis, and we check for that by replacing r theta with negative r negative theta. And so I've got r equals 2 cosine theta. We go negative r equals 2 cosine negative theta. We remember that cosine is an even function, so take a minute to think about what that means. That means that 2 cosine negative theta is going to have the same value as 2 cosine theta. I can multiply both sides by negative 1, so this is solved for r. I get r equals negative 2 cosine theta, which does not equal 2 cosine theta. So this fails the test for symmetry across that vertical axis. So now we're going to check for symmetry with respect to the polar axis. That's our horizontal axis. And this time, we replace r theta with r negative theta. So I'm starting with my r equals 2 cosine theta. I'm replacing, I get r equals 2 cosine negative theta. Again, because cosine is an even function, I know that equals 2 cosine, yes, positive theta. So this is symmetric with respect to the polar axis, that horizontal axis. And our last one, we are checking for symmetry with respect to the pole. That's the origin, basically. We're looking for that rotational symmetry. And here we replace r theta with negative r theta. So our r equals 2 cosine theta. I got negative r equals 2 cosine theta. Again, I'm going to multiply both sides by negative 1 to solve for positive r. R equals negative 2 cosine theta. So this again is a fail. Okay. We will check for symmetry as we move forward. It's going to help us as we graph, hopefully remove some of the work we have to do. So we are going to start plotting polar equations using points. There are 5 classic polar curves. Those are cardioids, limacons, lemniscates, rose curve, Archimedes spirals, and then we've got circles. Circles is the easiest of the polar equations to plot and graph, and we're fairly comfortable with circles in terms of plotting them on the Cartesian plane. A little easier here. So let's take a look at what this graph looks like. And again, so we're going to graph by plotting points, and that's exactly what I'm going to do here. So just a reminder, r equals 2 times sine of 0. Here's where understanding that unit circle helps. The sine of 0 is 0. So I get 2 times 0. So when theta equals 0, r equals 0. When theta is pi over 6, I got 2 times the sine of pi over 6. Sine of pi over 6 is 1/2. So when theta equals pi over 6, r is 1. R equals 2 times the sine of pi over 3. The sine of pi over 3 is square root of 3 over 2. So we get square root of 3 here, which is roughly, we're going to approximate 1.73 for the sake of graphing. At pi over 2, 2 times the sine of pi over 2. Again, I am producing more work here than you're probably going to want to. I just want to make sure you're clear with everything, where everything is coming from. So I got 2 times the sine of 2 pi over 3. Now, we did just show on page 1 that this should be symmetric across the vertical axis. That line theta equals pi over 2, which makes sense. Our sine values in quadrant 1 and quadrant 2 are both positive. They are the same. So I can crank these out fairly easily. 1, and at pi, I've got 2 times the sine of pi, which is 2 times 0. That gives me a 0. I stopped there, but let's go ahead and just crank out one more so we can take a look at what's going on here. The sine at 7 pi over 6 is negative 1/2. And so I get a value here of negative 1. So let's go ahead and graph these. Now, just like with the Cartesian grid, the rectangular grid, I can label those hash marks or tick marks, whatever I want. For the sake of making life a little easier for me, I'm going to make each of these circles 1/4. So here's 1, and here's my 2. Keep in mind that 2 was the largest value we had, so I'm not worried about going any further than that. Okay, so at 0, when theta was 0, I have 0. So right at the center. When theta was pi over 6, so here's my pi over 6. I had an r of 1, so I'm going out to 1. When theta was pi over 3, so now I'm here. My r was 1.73, so a little less than 1 3/4, so roughly here. At pi over 2, we're at 2. 2 pi over 3, we're back at 1.73. 5 pi over 6, I'm back at 1. And at pi over here, I'm back at 0. 7 pi over 6, it's a negative 1. So I'm not going this direction. I got to go the opposite direction along the negative, and it puts me right back here. So because of the way those values in the unit circle work, we can see as we move around the rest of our circle, we're just going to repeat and cover the values that we just hit. And so here is our circle. Let's see how close it gets in terms of, there we go, drawing that for me. Okay. So notice that 2 sine theta does give us a circle. It's symmetric across that vertical axis, that line theta equals pi over 2. It's got a point at 0, 0. It's got a point at pi over 2, 2. And the center is going to be halfway between those two. So we are going to take the next page to look at more graphs of circles and take a look at all the different ways we might see them.